We've talked a lot about the formations of mountains and volcanoes when plates are running into each other, or one plate is being subducted under another. But that isn't the only place. It is the dominant place, or the most likely place to find mountains or volcanoes on the surface of the Earth. But that's not the only place that mountains or volcanoes can form. And probably the biggest example of volcanic activity, or the most popular one, this might be a slightly American, Amero-centric point of view, but the most often cited example of volcanic activity away from a plate boundary is Hawaii. Hawaii. So this right here, these are the Hawaiian Islands. This is the big island of Hawaii, and it is experiencing an active volcano. Lava is, or magma is flowing from underneath the ground, and that once it surfaces, we call it lava. And that lava is actively making the island bigger. So where is that volcanic activity coming from? And then how can we think about that volcanic activity, or that kind of heat rising from below the surface of the Earth, to explain some of the geological features we see around Hawaii? So what we think is happening, and once again, this is all theory right here, is that Hawaii is sitting on top of a hotspot. In particular, the big island of Hawaii is sitting on top of the hotspot right now. And this hotspot, there's different ways, different theories on how it might emerge, but we think that at the mantle core boundary, and I don't know in this diagram whether they intended this white area to be the core, but let's just say that this is the outer core down here. Let's just say that this is the outer core. Outer core for the sake of explaining things. It's possible that kind of plumes of very hot material can kind of, just based on kind of the fluid dynamics of what's happening at that mantle outer core boundary, that plumes of really hot material can kind of rise up, let me do this in a darker color, can rise up from the outer core. They would rise up from the outer core and then create hot spots underneath the moving lithospheric plates, underneath the plates. Now, it's not necessary. We don't know for sure whether the hot spots are being created by these mantle plumes, this material formed or heated up at the outer core mantle boundary. But what we do feel pretty confident about is that there is this hot spot here, and it's independent of any of those convection patterns that we saw. I shouldn't say independent. It's obviously all related because we have all this fluidic motion going on in the mantle. But it's separate on some degree from all of those convection patterns that we talked about that would actually cause the plates to move. And to a large degree, or the way we think about it right now, this is stationary. This hotspot is stationary relative to the plates. And the reason why we feel pretty good about thinking that it's stationary relative to the plates is we see this notion right here. If you look at the volcanic rock in Kauai, which is one of the older inhabited Hawaiian islands, the oldest rock that we've observed there is 5.5 million years old, and it's all volcanic rock. Now, the oldest rock we've observed on the Big Island is about 700,000 years old. We also know that the Pacific plate, you could look at this diagram right over here, is moving in this general direction. In fact, we know it from GPS measurements. It's moving exactly in the direction that the Hawaiian Islands are kind of distributed in. So, frankly, the only good explanation for why we see this pattern, why we see newer land here, and then as we go further and further up the Hawaiian island chain, we see older and older land. And actually, if we keep going, we have the Leeward Islands over here. And as we keep measuring the rock on the Leeward Islands, they get older and older as you go to the northwest. And then if you even look at what's below the ocean, this is the Big Island of Hawaii. These are the main Hawaiian Islands. These are the Leeward Islands. But you see, even beyond that, submersed under the Pacific Ocean, you continue to see a chain of islands. So the explanation for what's happening here is that you have a stationary hotspot that is right now underneath the Big Island of Hawaii. And I just want to be clear. The Big Island is called the Island of Hawaii. It is one of the islands in the state of Hawaii. So I don't want to cause you confusion. So I'll just call it the Big Island from here on out. So the hotspot is right under the Big Island. But if you were to rewind 5 million years ago, if you were to rewind 5 million years ago, the entire Pacific plate was probably on the order of, about 150, 200 miles, however far Kauai is from the Big Island. It was probably shifted that much to the southeast if you go back 5 million years ago. So 5 million years ago, when all of this was shifted down and to the right, then Kauai was on top of the hotspot. And so this is how each of these islands are formed. If you rewind a ton of years, then maybe this area over here on the Pacific plate was over the hotspot. An island formed there. Then the Pacific plate kept moving to the northwest. It kept moving to the northwest, and new islands, new volcanoes kept forming. Those volcanoes would release lava that would keep piling up, eventually go above the surface of the water and form this whole chain of islands. And as the whole Pacific plate kept moving to the northwest, it kept forming new islands. Now, the one question you might ask is, well, how come the Big Island is bigger? Has the plate kind of paused over there? Is it spending more time over the hot spot so that more lava can kind of form there to form this? Essentially, it's an underwater mountain that's now also above the water. And actually, if you go from the base of the Pacific Ocean to the top of the Big Island of Hawaii, it's actually 50% higher than Mount Everest. So you could really just view it as a big mountain. But the question is, this looks so much bigger than Kauai, and they keep getting smaller as you keep going to the northwest. Is somehow the Pacific plate slowing? Is it spending more time here? And the answer is it's probably not slowing. What's happening is, at one time, Kauai was also probably a relatively large island. If you rewind maybe 5 million years ago, Kauai also might have been about that big. But over 5 million years, it's just experienced a ton of erosion. Remember, once it moved over the hotspot, new land wasn't being created. It's in the middle of the Pacific Ocean. It's experiencing weather. 5 million years is a long period of time. And so it just got eroded over that time. So the older the island is, the more eroded it's going to be, and the smaller it's going to be. So if you go to these underwater mountains up here that don't even surface above the ocean, at one time they might have surfaced, but due to the ocean and weather and whatnot, they've just been eroded over time to become smaller and smaller kind of remnants of volcanoes. So anyway, I thought you would find that entertaining of how the Hawaiian Islands actually got formed, and how we can actually have these hot spots and this volcanic activity, and actually even earthquake activity outside of actually plate boundaries. Actually, while we're looking at this diagram, we talked about the trenches at plate boundaries. You can actually see it here because this shows the depth, and the really dark blue is really dark, deep parts of the ocean. So this right here is the Mariana Trench, and you can see over here the Pacific plate just getting abducted, or not abducted, getting subducted into other plates underneath, and forms these trenches here. Anyway, hopefully you found that entertaining.
In geology, the places known as hotspots are volcanic regions thought to be fed by underlying mantle that is anomalously hot compared with the surrounding mantle. They may be on, near to, or far from tectonic plate boundaries. Currently, there are two hypotheses that attempt to explain their origins. One suggests that they are due to hot mantle plumes that rise as thermal dye appears from the core mantle boundary. An alternative hypothesis postulates that it is not high temperature that causes the volcanism, but lithospheric extension that permits the passive rising of melt from shallow depths. This hypothesis considers the term hotspot to be a misnomer, asserting that the mantle source beneath them is, in fact, not anomalously hot at all. Well-known examples include Hawaii and Yellowstone. The origins of the concept of hotspots lie in the work of J. Tuzo Wilson, who postulated in 1963 that the Hawaiian Islands result from the slow movement of a tectonic plate across a hot region. Beneath the surface, it was later postulated that hotspots are fed by narrow streams of hot mantle rising from the Earth's core mantle boundary in a structure called a mantle plume. Whether or not such mantle plumes exist is currently the subject of a major controversy in earth science. Estimates for the number of hotspots postulated to be fed by mantle plumes has ranged from about 20 to several thousands over the years, with most geologists considering a few tens to exist. Hawaii, Reunion, Yellowstone, Galapagos, and Iceland are some of the currently most active volcanic regions to which the hypothesis is applied. Thank you for watching. For more educational videos, please subscribe to Wiz Science on YouTube or visit wizscience.com.
Hotspots are deep-seated sources of heat and magma that extend from depths as deep as the core mantle boundary and generally stay fixed relative to plate motion. The plate moves across the hotspots, but the hotspot doesn't move. Volcanoes are left behind in tracks that show us the direction and speed of plate motion. As this image shows, some hotspots form through large amounts of heat that are injected into the lower mantle and cause melts to form. As these melts are less dense, they rise. More mantle melts and the plume grows a large, mushroom-shaped head. When it finally hits the surface, the magma collects under the rigid lithosphere and pressure builds. Cracks open up in the lithosphere and allow the magmas to erupt on the surface in a massive eruption of basalt that floods the surface. These basalts from the head of the plume can take over 1 million years to completely spill out, covering areas as large as Texas, with kilometers-thick piles of dense basalt. We call these massive initial hotspot eruptions flood basalts, and they have been associated with major mass extinction events, including the extinction of trilobites, ammonites, and later the dinosaurs. When the head of the plume has finished erupting, the main stalk of the plume continues to erupt for potentially hundreds of millions of years. Though these eruptions are much less massive than the initial flood basalt eruption, they still produce more volcanic material and activity than subduction zone volcanoes or divergent plate boundary volcanism. As they erupt, large volcanic mountains form on the surface, continually fed by the large amounts of magma. Eventually, however, these volcanoes are moved away from the hotspot as the plate moves, and when they get far enough away, a new set of cracks and conduits will form, and a new volcano will take the place of the old one. So we can study these hotspot tracks and from them learn both the direction and speed of plate motion. A good, somewhat local example is the Yellowstone hotspot. The Columbia River basalts are the flood basalts that mark the initial eruption of that hotspot. Here is the location of the hotspot and the active volcanism in North America today. Here are the older volcanoes the hotspot produced before the plate moved them away. Where was this older volcano when it formed? Right up here where the active volcanism is today. So what direction did it move? This way. And thus this arrow represents the general direction of movement of the North American plate over the past 9 million years. And how fast has it been moving? If we know that the volcano is 9 million years old, and we can measure the distance it has traveled since it formed, 270 kilometers, we can calculate a speed. 270 kilometers in 9 million years is roughly 30 kilometers per million years. To convert to a more useful unit, centimeters per year, we have to convert kilometers to centimeters and millions of years to years. That ends up canceling out a lot of zeros and being the same as dividing by 10, so 3 centimeters per year, similar to what we mentioned earlier for the spreading rate of the center of the Atlantic Ocean. Pause now. This map shows other major hotspots across the planet and the identified flood basalts that connect to them. Notice 2 other important examples, Iceland and Hawaii. Iceland is unique because it sits atop the mid-ocean ridge, which means there are 2 sources of magma there, seafloor spreading and hotspots. It also means that the island formed never really moves away from the hotspot, but only grows wider. In the Hawaiian Islands, we see here the active island, and as we move northwest, the islands get older and more eroded, smaller, and eventually becoming submerged seamounts that make up the Emperor Midway chain. Can you tell the direction of motion of the Pacific Ocean from this track? Pause and think about it. Pause now. Two interesting things we see when we study this track closely. 1. Notice the bend that happens about 45 million years ago. What would cause that? The Pacific Plate has been moving in one steady direction for the past 45 million years, and prior to that it moved also in a steady direction, but a different one. What happened 45 million years ago to cause the entire plate to change direction? We'll review the answer at the end of the lecture. The other thing that we see with this track is that the islands seem to be entering the subduction zones of the Aleutian Arc. What's happening there? Terrain accretion. A train wreck, so to speak. Pause now. And now, the answer to the direction change of the Pacific Plate. The only thing that can cause such a major shift in direction of a plate is if an obstacle blocked its path and it had to be diverted. What would have caused that? What major obstacle? India collided with Asia, and when it did, every plate on the planet had to shift to accommodate the major obstacle that formed in the middle of the road. For more information and more detail, continue on to the next video in this series.